Namaste, welcome back to the Pragna channel. You are watching Machine Learning Basics Theory playlist. And this in this video we are going to learn about long short-term memory, or in short LSTM. If you watched the previous video about recurrent neural networks, you know where the recurrent neural networks lacks and how you can use long short-term memory in that place to resolve, or not to resolve but to handle such scenarios. What is long short-term memory? This is another type of, not, I wouldn't say this is another type of, but this is a type of recurrent neural network architecture designed to process and predict sequences of data such as time series or text. So previous one recurrent, but that is, we would call it standard, correct? Standard RNN, where we had only input, hidden, output. But this had a problem, not a problem, but this couldn't handle all the scenarios. If you have to remember it for a long time, this couldn't do it. That's where this one comes into picture, correct? LSTMs are specifically built to overcome some of the limitations of the standard RNN, particularly their tendency to forget information over long sequences. Short sequences, this is fine, but if there are long sequences, then standard RNN had a problem, and that problem is known as vanishing gradient problem, and this is designed to specifically handle that. Okay, so you can see that here. So how does this work? We have already seen how RNN works, but how does this work and how does this overcome the vanishing gradient problem? LSTM networks are designed with a memory cell that can maintain information in memory for long terms. What is it called? It's called memory cell. If you remember, RNN doesn't, the standard RNN doesn't have it, but this one has it, so that this can store it for long periods, which is crucial for tasks where context over time matters. The LSTM cell has several key components. Okay, this particular memory cell has key components. What are those? Cell state, you can see something here in this diagram, and then it has something called gates. You can see forget gate, input gate, and output gate. The cell gate, which is the memory of LSTM that carries information across the sequence. The cell state can be thought of as a conveyor belt that runs through the entire sequence with only minor linear interactions. It's what allows LSTMs to remember information over long sequences. And these gates, the LSTMs, are use three types of gates to control the flow of information into, through, and out of the cell. What are those? Forget gate, input gate, and output gate. Forget gate decides what information should be discarded from the cell state. Input decides which information should be added to the cell state, and output gate decides what information from the cell state should be output at the current time step. These gates enable the LSTM to selectively remember and forget information, making it highly effective at learning from sequences where both short-term and long-term dependencies are important. Okay, so now you know how it works, when you should use this instead of your standard recurrent neural network. Now it comes to real life examples, and again these are like basics. I'm not teaching you advanced, as the playlist name itself is called Machine Learning Basics, so I'm not going to go into how the algorithm is written, etc. So if you are interested, you can go ahead and learn that in depth in books, not here. But yeah, so that's what the LSTM is all about. And again, you would see similar kind of scenarios like RNN, but more a little bit different ones. What the first real life example is text generation, and the scenario is generating poetry or song lyrics. LSTM networks are trained on a large corpus of text, let's say Shakespeare's plays or song lyrics. After training, the LSTM can generate new text that mimics the style and content of the input. The LSTM captures the structure, syntax, and even some semantic elements by remembering the sequence of words and how they relate to each other over long distances. Don't you think that's awesome? So outcome is produces that mimics in our case Shakespeare and content of training data. Even though Shakespeare is not here anymore, using this kind of algorithms, machine learning, we can try to mimic his work. I mean, of course, it's going to be mimicking, not exactly what he would have written. And time series forecasting, like predicting stock prices, we just discussed in the other one as well. LSTM networks can be used to predict future values in a time series, such as stock prices, weather patterns, or sales data. For instance, an LSTM could be trained on historical stock price data to predict future prices. The model learns to recognize patterns and trends over time, even when the patterns are complex and involve dependencies across many time steps. You might be thinking we use the same use case there as well, but remember, over long period of time that won't work, but it has that gradient problem where the LSTM shines. And then speech recognition, converting spoken language to text. In speech recognition systems, LSTMs are used to model sequences of audio data where each time step corresponds to a fragment of the speech signal. The LSTM can learn to recognize and transcribe words and phrases by understanding the context of sounds over time. Over time is important because that's where this shines. Over time, helping to differentiate between similar sounding words based on their context. Outcomes, powers, voice activated assistance, Siri again, and transcription services. And another anomaly detection in sensor data scenario would be predictive maintenance in manufacturing. In industries like manufacturing, LSTM networks are employed to monitor sensor data over time and detect anomalies that might indicate equipment failures. For instance, LSTMs can be trained on normal operational data from machinery and then used to flag unusual patterns that could signal an impending breakdown, enabling preemptive maintenance. And then the final example would be language translation. Here you can translate text from one language to another. In machine translation, LSTM networks are used as part of sequence to sequence models where one LSTM processes the input sentence in the source language and another LSTM generates the translated sentence in the target language. The LSTM's ability to remember long-term dependencies allows it to maintain the context of a sentence, which is crucial for accurate translation. So applied in translation services like Google Translate. So, but why LSTM? Why? Because simple, it handles long sequences. LSTM networks are designed to handle sequences where important information can be spread out over long distances. They can remember information from earlier in the sequence, which is crucial for tasks like language processing, where the meaning of a sentence often depends on words that appear much earlier. And it avoids vanishing gradient problem, which is the problem with the standard RNN. LSTM's design mitigates the vanishing gradient problem, which is common in standard RNNs. This allows LSTMs to learn from sequences more effectively, even when they are long and complex. And finally, adaptability. LSTMs are versatile and can be applied to a wide range of problems involving sequential data, from predicting time series data to understanding natural language. And let's come to the summary when we finish our scenario-based step-by-step explanation. And the example we are going to pick is that Shakespeare's song lyrics, generating new lines of poetry or song lyrics that mimic the style of the input data. And the example task, we train an LSTM model on a data set of Shakespeare's sonnets to generate text in a similar poetic style. And what will be our first step? Prepare the data set. Okay, and our text data will be a collection of Shakespeare sonnets or song lyrics, and example text would be this: shall I compare thee to a summer's day, thou art more lovely and more temperate. Text processing and preparing, the as part of preparing the data set, you will do text pre-processing. As part of this, you will do the tokenization, which is splitting the text into individual characters or words, and then it will have a list of words, characters and words. And then next step is creating sequences, right? Sequences of characters or words used as inputs to predict the next character or word. Example sequences would be, for example, if the input is shall I comp, then it will predict the output A in case of character. And if you have given hall I compa, then it will give you R. Now, next step as part of this would be vocabulary creation. Similarly, in previous example, we have assigned an index. Even here, there we have assigned an index to the words. Here you will assign an index to the character, because this one can predict characters as well as words. So as you can see, shall, whatever text you are seeing, each character is given an index. Again, it depends on what you are trying to achieve. If you want character level, you will do this. If it is word level, then you will index the words. Okay, so converting your text to numerical data, which is what we are doing here. Once you prepare your data set, second step will be building LSTM model, correct? And then LSTM model, similar to our layers, input layer, then here you will have a LSTM layer, and then you will have output layer. Input layer receives the input sequence of characters or words. LSTM layer process each element in the sequence, maintaining and updating the cell state as well as hidden state. The standard RNN only updated hidden state, but here you will also update the cell state. And output layer outputs the predicted next character or word after processing the entire input sequence. Correct? So if we have to look at how it looks, the training, sorry, this is building, then we will train the LSTM model. Okay, the time step, first one is what? Forward propagation. As part of the forward propagation, time step 1, it processes the input character S, then it will update the hidden state as well as the cell state. And second time step, the letter H, again hidden state, cell state, so on and so forth, as you can see here. Now here what are we doing? We are predicting the next character, and my input, as I said, was shall I comp. Okay, then it is supposed to predict A or E. I mean, depends on later on, but it should predict A. So now as soon as it processes P, then it will predict the character A, which you can see here. Again, based on the loss calculation or compute the error between the predicted character and the actual next character, what will you have? You will have backward propagation, correct? I mean, you did the forward propagation, then you will have backward propagation, which is adjusting the weights and biases through back propagation to minimize the error. Okay. And next we are going to evaluate our model. Okay, so how do we do that? Qualitative evaluation by answering, does the generated text mimic the style of the original data? That's what qualitative evaluation you will call it. And quantitative metrics, it's a measure of how well the model predicts the next character. And that you can see here, similar to the previous one, where you have accuracy and the loss over time. So this one shows the increase in accuracy, as you can see, as the model trains over more epochs, indicating that the model is improving its ability to predict the next character in the sequence. And loss over time illustrates the decrease in loss during training, showing that the model is learning and minimizing errors over time. So I don't think I have to explain further. We already discussed in the previous one. So in summary, this is ideal for tasks involving sequential data such as time series, speech recognition, text generation over longer sequences, and the ability to process and remember information over long sequences, making it crucial for accurate predictions and outputs. So this is LSTM. And the next one is about GRU, which is another method of RNN. We will talk about when would you use these two as well as part of the next video. So I hope you enjoyed this particular lecture. If so, don't forget to subscribe, like, and comment. See you in the next video. Have a great day. Peace out.